Hi, in this video I'm going to do some practice problems with the integrated rate laws we learned in the previous video. So first it says the decomposition of nitrogen dioxide at high temperature is this formula. NO2 makes NO plus 1/2 O2. Second order reaction. Now I told you it's second order. If the rate constant, it also told you the rate constant. So now if we refer back to the previous video, second order will be 1 over concentration of A at time minus 1 over concentration of A initial equals KT. Now K we're given as 3.4. And it said the concentration to decrease from 2.0. So we know the initial as well. And we're looking for the time needed. We're looking for this T. So first let's start plugging numbers in. 1 over A slash initial is, so initial is 2.00 and we're going from 2.0 to 1.29. So our time is going to be 1.29. Our concentration after a period of time will be 1.29 minus 1 over the initial concentration, which is 2.00, equals K, which is 3.4 times T. Now all I have to do is plug that into a calculator. 1 over 1.29 minus 1 over 2. Again, I got the 1.29 from, because it said the decrease is from 2 to 1.29. That means 2 is the initial, and 1.29 is A of T, which is the concentration of A after a certain amount of time, and we're looking for the time. Now, we divide that answer by 3.4 to get T. We solve this equation and divide this part by 3.4 to find T, and we get T as 0.0809. And this will be minutes because our rate constant is molar per minute. So our units will be minutes. And if you want to see how much seconds that is, basically multiply by 60. Number 26. The decomposition of N2O5 is a first order reaction. Okay, now we know it's a first order reaction. And first order reaction, we use the formula. This A concentration of A over time minus Ln log natural log of A, the initial concentration, equals negative KT. And here it said initial is 2.56. So initial is 2.56 milligrams. And then 2.50 milligrams after a certain amount of time. So our A of time will be 2.50 mg. And the time is 4.26 minutes. Do we care about the temperature? Not at all. Now we define K. Notice how these two are not giving concentration and instead milligrams. So, and with a given amount of information, we do not know how to convert them into molar concentration, right? Because we're not given liters, and concentration is moles divided by liters. If we're not given liters, we can't find the molarity. However, notice how both of these ends with the unit of milligrams. In that case, whatever the volume is, when we divide it, the ratio is going to be the same. They're going to be divided by the same thing, and the unit will remain the same as well. So in this case, we actually do not need to use the concentration. We can straight up use the numbers as we're given. So Ln, concentration of A of T, we can use the mass of A at T at a certain time, which is 2.50, minus Ln. Now we need the initial concentration, but we're not given concentration, so we're going to use the mass of the initial. And because they're both in milligrams, that's why it will work right now. They're both in the same. They're both milligrams, and that's why they're both milligrams, and that's why we'll be able to use them instead of the concentration. Now we'll set that equal to negative K times time, which is 4.26 minutes. Now this is also plugging into your calculator. Ln of 2.50 minus Ln of 2.56 divided by 4.26 gives an answer negative 0.005567 equal to negative K, and K is equal to 0.00557. And what will the formula be? What will the unit be? The unit will be minutes to the negative first power for K, since this is the first order reaction. And then finally, we have number 27. How long will this decompose the first order reaction. So again, we're told it's a fourth order, so we're going to use the law for first order, which is ln a of t minus ln a initial equals negative kt. That's how much we're given. So we're given k. K is equal to 1.6 times 10 to the negative third, and we're also given that 81% of the sample decomposes. So we can assume that A of initial will be 1 molar, and after a certain amount of time, 81% will be decomposed, making it. And after a certain amount of time, 81% will be decomposed, and that's basically remaining 0.19 molar. Now all we need to do is look for the time. So Ln concentration of after a certain time, after 81% is decomposed, that's only going to leave us with 19%, which is 0.19 molar, minus Ln of initial. In this case, we're assuming with 1 molar because we're not giving any information at all about that, and we can make that equal to negative 1.6 times 10 to the negative third power times time. Now we do plug into our calculator. Ln natural log of 0.19 minus the natural log of 1 divided by negative 1.6 e to the negative third. That gives an answer of 1037.96. Okay, actually we don't even need the 0.9. It rounds up to 1038, and if you want to stick to the rule of 3, it's going to be 1040. Now, what's the units? Well, since in the problem, it didn't tell us any units at all. It didn't tell us if it's minutes to negative first power or seconds to negative first power, or how much seconds or minutes it will take. So right now we only know that is 1040 at a certain for a certain time, whatever the unit of the time will be. If the question gave us more information, we wouldn't know if it's time or if it's seconds or minutes or etc. But right now all we know is that a time constant of 1040. Thank you for watching.